Hi everyone, my name is Francois, and today I'm going to be talking to you about fair unsupervised learning. This is John Work with Islam Utyagulov. First of all, a disclaimer just to state that this work represents only our own personal opinions and do not reflect anything else. So unsupervised learning is at the heart of many machine learning applications, and frankly, we can think of it as either a standalone sort of model, and one could think of principal component analysis or variational autoencoder, or it could be part of a pipeline, right? So it could be just some layers within a large neural network, or it could be a preliminary step, for instance, when we want to run principal component regression. So a lot of research has been carried out in terms of fairness around principal component analysis, also around k-means or around spectral clustering. So sort of really the two challenges that are at hand is one, to define sort of fairness metrics for unsupervised learning. And we do not really delve into this particular problem. It is far from trivial. And the second one is to provide a generic framework that is going to encompass many unsupervised learning algorithms to be able to provide a generic framework. And so we do this, and we do this in the case of generalized low-rank models. So generalized low-rank models, or GLRMs, are an approximation of a data matrix by two low-dimensional factors. So in short, we would suppose that Aij is equal to the dot product between a vector xi and a vector yj. And so the definition of a generalized low-rank model is simply to put a loss function between the true value of the matrix and the value of that particular dot product plus some regularization terms. And interestingly, this framework recovers many usual algorithms, again, PCA, even robust PCA, k-means, and so on and so forth. So now let's move on to the notion of fairness in unsupervised learning. So we've tried to categorize them broadly into three different columns, right? The first one is the pillar on social fairness. And the notion there is that the average cost, so the reconstitution error between the matrix A and, let's say, the dot product xi, yj, has to be the same across groups, at least on average. And this can typically be achieved via a variety of ways, one being to minimize the worst group average cost. The second pillar has to do with balanced fairness, and this has to do with the distribution, actually, of the outcome as opposed to really the cost function itself. And so it is saying that different groups should have the same distribution. So for instance, for clustering, if we come up with two different clusters, then the two different groups should have the same distribution across clusters. And there are similar concepts such as bounded representation or maximum fairness cost. And last, there is individual fairness, which states that two similar inputs should have fairly similar outputs. And so the point is that all of these different approaches can be tackled via our framework, but we're going to focus first and foremost on social fairness. So before moving forward, let us also define a group functional. So a group functional that we've called T simply regulates the trade-off between the group-wise average losses. So if we suppose that we denote by Zi the average loss in group I, then what we see is that we wish to understand how we are going to trade off the loss in group I versus the loss in, let's say, group K. And so to do so, we can see that many group functionals have already been proposed in the literature. So the first one, for instance, is just a weighted average. The second one that we've already touched on is a notion of a maximum. So we're going to try and maximize the maximum cost, and this is linked to the theory of justice by John Rawls. Another approach is an LP norm, and last but not least, we can also simply penalize any discrepancy between group losses, right? And this is the last term that we can see here. Importantly, losses can be multivariate. They can be different depending on the exact fairness definition, going back to our previous slide, and they can combine all those types of definitions. And so there are really interesting sort of framework again. So we propose just one particular fairness functional in this work, just for the sake of simplicity, and we consider the weighted log-sum exponential. So log-sum exponential is used throughout machine learning and reinforcement learning, so it is well known, and importantly, it is a soft maximum in the sense that it can approximate the max of a given vector as we take a given parameter, here alpha, to infinity. So we propose a weighted log-sum exponential, which has a lot of nice properties, and this is why we recommend it. One is that it's jointly convex in the losses, which means that if the losses themselves are convex, then the overall loss is itself convex, or biconvex in our case. And also, as mentioned, that as we take alpha to infinity, then we recover the max function. Last but not least, there is a shift property that holds, which is quite interesting, whereby we can subtract sort of a mean from the vector and recover an additive structure. So this is a very natural interpretation in the case of fairness, whereby we try to minimize an average cost plus a notion of disparity between groups and that average cost. So how can we fit a fair generalized low-rank models? Well, there are really two generic algorithms to do so, and many more that can be bespoke. But the first one has to do with alternating minimization. And so fundamentally, this is the same as for fitting a generalized low-rank model. So it actually does not make anything more difficult. And the other one is a biconvex gradient in the sense of gradient descent. And this would require that the overall loss is itself biconvex, which means that the low-rank, generalized low-rank model, the initial one, should be biconvex. So this would be the case, for instance, of an SVD. So now let's move on to some of the key results, and I will spend a little bit of time on those. So the first one is that we do recover a trade-off between the loss function and fairness. So as we can see, we've plotted here across 3 data sets, so the adult data set, the German credit data set, and the loan defaults data set. The different points linked to k-means. So we apply k-means in all of these situations, but what we do is that we use a weighted log-sum exponential, and we vary the hyperparameter alpha. Again, the closer it is to 0, the closer we are to just an average, and the closer to infinity, the closer we are to a maximum. And so what we can see, as expected, is that as we increase the fairness requirement, the average loss itself increases, which we see here, which is quite well illustrated. So this is similar to some of the results that already exist in supervised learning and that have been well established, that the more fairness we require, the more we tend to lose in terms of statistical performance or accuracy. Now, another finding that is really of interest and I think is very important, especially for unsupervised learning and for online learning, is what happens when we consider out of sample. So there is no natural definition of out sample in general for unsupervised learning. That has to do that applications such as PCA or k-means would typically require looking at the overall data set. However, in online learning, for instance, what would tend to happen is to actually freeze some of the factors and only let the weights be fitted. So if we actually go back to the definition of a fair GLRM, then what we would see here, for instance, is that we would actually freeze the yj and leave the xi free. So the yj would be fitted on the training data set, and the xi would actually come from the out of sample and would be fitted on the out of sample. So if we go back to the results that we have obtained, what we can see here, and which is somehow surprising, is the fact that in that case, we do not necessarily recover a better or a lower group outcome disparity as we increase alpha. So what that means is that the out-of-sample behavior is different and reflects the fact that sometimes choosing an intermediate trade-off as opposed to necessarily picking alpha is equal to plus infinity may be beneficial. And we see that across at least 2 of the data sets. Even on the first data set, we see a very strong elbow, which would suggest that we might want to pick a lower alpha. This is linked to some of the results that we have seen recently in supervised learning, which point to the fact that generalization and out-of-sample behavior in fairness are quite important. They represent a new type of trade-off in the sense that trying to fully debias an algorithm may actually lead to poorer or worse out-of-sample fairness performance. So in conclusion, I think we have proposed a straightforward framework to handle a fair variant of generalized low-rank models. And so this is quite handy as it can be used for PCA, k-means, subspace clustering, robust PCA, matrix factorization, non-negative matrix factorization, and so lots of different applications. We've introduced the concept of fairness functional, and we've just proposed one, but what's really important is that we can take those 2 ingredients and we can take model coming from the generalized low-rank model family. We can take a fairness functional, and then we can apply one of the algorithms, such as alternating minimization, and we will get some of the results. So this, if you want, is very straightforward and leaves modeler the choice to select whichever they think is the best option. Lots of details were omitted here, so please refer to the paper where all the derivations are presented. But last but not least, I think a lot of research is required in the field of unsupervised learning. So the first one is to examine the various fairness definitions in unsupervised learning, and as we document in the paper, we can have fairly different results depending on the fairness metric that has been chosen. So in particular, social fairness can lead to something very different from, let's say, bounded representation. And the second point is a notion of out-of-sample behavior when debiasing algorithms in unsupervised learning. And so we believe that is really key, in particular, to be able to quantify trade-offs between loss and disparity, for example, as we see that the results tend to point to the direction that intermediate values of hyperparameters lead to better and more robust results. And so this is something that should probably be explored in depth in the field of unsupervised learning, as the notion itself of out-of-sample is far from trivial. Thank you very much for your attention.